7 factorial. So what's going on in the numerator here? I'm choosing the 5 people who will receive the correct heads, or 5 numbers which will be fixed in their natural positions. You can think of it in different contexts in this way. And the remaining 2 will have to be the duration. There's only one way to do it. So this is 1. So this is just 7 to 5 divided by 7 factorial. Exactly 6 men receive correct heads. 0. This is impossible. You cannot just give 6 men correct heads.
You just don't return the other half.
Okay. There were another group of questions I wanted to look at. Okay, so that's that. So let's look at a few more examples from the book. And that is number 14. So we are asked to find the number of permutations of 1 to n, in which exactly k integers are in their natural position. Because you know the answer to this now very well.
So, and choose k.
So and choose k, so choose the k integers to be fixed. Yeah?
Derangement of n minus k.
And then do the derangement of n minus k. Here, the numerator corresponds to that situation. 7 choose 5, and 2, which is the numerator. We've done similar examples in inclusion-exclusion principle. Of course, this is just finding the number of derangements is just inclusion-exclusion. It has the same flavor as, remember we had numbers 1 through 8, and then in how many ways the even integers are fixed or odd integers are fixed. So this is a very, it's a similar situation basically. So this is say, the integers fixed and the range. Okay, so this is number 16, where we are asked to give a combinatorial proof of the following identity. So n factorial is equal to k from 0 to n choose k, dn minus k. Here we define d0 to be 1. Okay. So let's do the proof here. So n factorial, of course, the set of all permutations. This is what the left-hand side counts. So all we need to do is just find a clever way to split these permutations into parts, which is not so hard to believe that this is exactly what you're going to get for each k, and then you take the union of them. So let's write this down. So let S to be the set of all permutations of n letters and numbers. Okay, so we have the size is n factorial, of course, which is the left-hand side. So now we just split it. So for each k with 0 less or equal to k less or equal to n, I can consider s of k. And that's going to be the permutations in S. So from the set of all permutations in which exactly k integers are fixed. Fixed meaning they're in their natural position, in other words. Observe that, of course, k can be 0, which means that nobody is fixed. So I have s of 0, and then s of 1, one integer is fixed. S of 2, exactly 2 integers is fixed, are fixed. Now notice that there is no overlap. This is a partition of the set because of the word exactly. Okay, so I'm not going to have an overlap of S1 and S3. Alright, so that means I have a disjoint union of these sets as the set of all permutations, in other words. And it's important that this is a disjoint union. Because it's a disjoint union, the right-hand side, the cardinality of the right-hand side is just the sum of each pieces in this union, side of the x of k, in other words. So I can say that this is equal to, by the addition principle. Okay, fine. We still need to count these things. So exactly k integers are fixed, which is down in a previous question. By example 4. Begin with 1, 2, and 3 in some order. Okay, so what do you say? So the restriction is these three numbers, 1, 2, and 3, to be in the first three positions, right? So I wanted them to begin with those permutations where 1, 2, 3 are in the first three positions in some order. So we're allowed to permute them, paying attention to the fact that we should still get a derangement. So 1 to 3 is not okay, for instance, or 3 to 1 is not okay to have in the first three positions. And then you will also have the remaining guys, 4, 5, and 6 to be arranged. So what do you say?
Arrangement is 3 times arrangement of 3.
The arrangement of 3 times the arrangement of 3. So you put 1, 2, 3 in the first 3 positions as a derangement, of course. Okay, so you get a total of B3. And this is 2 ways to do it. And then in the second step, the arrangements of 5, 4, and 5, 6. This is also 2, so the answer is actually B3 times B3, which I can do here, but this is also and you can easily list them, of course. Okay, so that's about what I wanted to say in 6.3. So for the quiz, just 2 examples. One is about a bunch of other examples in the beginning, but they're all very much the same, particularly because in any case this couldn't be in the quiz. So I'll ask you some kind of counting of this sort, basically. Either an inclusion, exclusion, or reduction. So let me get started. The last thing I want to do is 6.4, and this is forbidden positions. Limitations with at least explaining what the idea is for given. So the idea here is this is a generalization of the arrangements. Okay? So remember what we were doing, you're looking at permutations of 1 through n where the first position is not 1, the second position is not 2, etc. Now what you want, rather than taking this one element set, which is 1, 2, 3, you want to take general subsets of 1 through n and say that these positions are not allowed to be occupied with these numbers. So this is the idea. Okay, so that corresponds to looking at permutations when there are forbidden positions, in other words. Okay, so let x1, x2, xn be possibly empty. Okay, so let's just write it this way. Subsets of 1 through n. And they may intersect, they may possibly be empty, so let me write it here. They don't have to be disjoint at all, as you will see in the examples. So one defines the following thing. Capital P x1 through xn is all permutations by definition of 1, 2, all the way up to n, such that, but I want to write actually all permutations I1, I2, I sub n, there's no comma here, of 1 through n, such that I1 isn't allowed to be from the set x1. I2 is not allowed to be from the set x2, etc. Observe that when x1 is a one-element set 1, likewise when xi is a one-element set subset I, that's exactly the arrangements. This is what it corresponds to. Okay, so in other words, elements of xi, looking at it from the other way around, are not allowed to occupy position I. That's what this says, right? All right? And then you let small case p to be the number of these cases. Okay? Let me go ahead and write a special case here. If xi is I, then of course what we get here is the arrangement. Right? And these are your forbidden positions, xi's. So let's just look at an example.
Still have a couple more minutes.
So let's say n is equal to 3, x1 is equal to 1, x2 is equal to 2 and 3. And x3 is empty. So what is this set now? All permutations I1, I2, I3 such that I1 is not equal to 1. I2 is not equal to 2 and 3. And there is no restriction on I3. Anyone is allowed to occupy the third position. So now what do I get? Let's write them down. So if I2, the second position, cannot be 2 and 3, what is it going to be? It has to be equal to 1. I have no choice here. If the first one is not equal to 1, what are the choices for the first one? 2 or 3. Because there is no restriction on I3, we can now write down what do we get. So we have two possibilities. We can have 2 in the first position, this is always 1, and then the remaining one will have to be 3. Or you can have 3 here, the second one is always 1, and the last one now is going to have to be 2. Okay? Now, this is a simple case of what we are looking into. Just picture, next time I'll write another example. These guys can intersect, etc. So you can picture a much more real situation. Ultimately, the way to treat this is going back to the rook arrangements and thinking of putting rooks in the chessboard so that there will be forbidden positions corresponding to the xi. Read this section in the book a little bit because I'll probably need to be a bit quick here because of time constraints. So I'll try to streamline it, but if you read it, it will help. And you may ask,